Welcome back. In the previous example of the free-falling body, we assumed that the drag force was proportional to the instantaneous velocity v in the form of kv. However, for those of you who have already studied fluid mechanics, or for those who might study fluid mechanics later on in their studies, we'll see that the drag force is actually more accurately modeled as being proportional to the squared of the velocity. That is, we could write it as the drag force is equal to some constant c multiplied by v squared. Typically, that constant c has geometric properties as well as properties of air such as density and viscosity. So for example, a body that is larger, that has a larger cross-sectional area, will have a larger c than a smaller body that does not actually have much of a drag force acting on it. So what does this more realistic drag force lead us to? So recall, we used Newton's second law, but now, instead of mg minus kv, we have mg minus cv squared is equal to the mass times the acceleration. So putting this in a standard form, we would have the mass times the acceleration plus the drag force will be equal to mg. And again, what we're doing is that we're leaving mg, which does not multiply the dependent variable v, on the right-hand side of the equation as our non-homogeneous term. We can divide this by m to put it in a somewhat standard form, which will give us dv by dt plus c over m v squared is equal to mg. So note that we can no longer apply the integrating factor method. Recall that the integrating factor method applies only to first-order linear equations. However, we have a pesky term over here, which is nonlinear. So we need a new method to solve this more accurate form of a free-falling body. So this leads us to our study of nonlinear first-order differential equations. The study of nonlinear equations is much more involved than that of linear equations. We run into issues such as the existence of solutions and whether the solution is unique. That is, are there other possible solutions to the same problem with the same initial conditions? So in the next few videos, we will look at some strategies to solve nonlinear first-order equations. In this video, I want to talk about the separable first-order equations. So this method applies to both linear and nonlinear equations. So let's write a differential equation as follows, in a very compact form. So we'll write something like y prime is equal to some function h, which is a function of x and y. And we say that it is separable if the right-hand side, h of x, y, can be written as f of x over g of y. Now don't take this too literally. All we are saying here is that we can separate the right-hand side as two distinct functions, one that groups only the x terms and the other that groups the y terms. This allows us to write our ODE as follows. We'll have y prime is equal to f of x over g of y, which allows us to separate the x and y terms on either side of the equation. So we can multiply both sides of the equation by g of y, which will give us g of y, y prime, is equal to f of x. So we can directly integrate this. So we have g of y, and then so recall that this y prime is dy by dx. So if we multiply both sides by dx, we're left with dy, and that is equal to f of x dx. And of course, because this is an indefinite integral, we will have a constant of integration c. Now, this compact form is very easy for us to separate. However, keep in mind that to put an ODE in separated form might involve some algebraic tricks. And sometimes it can be quite involved. And we'll take a look at a few examples. So let's look at a very simple example right now, where we have a simple ODE of the form y prime is equal to 2x multiplied by y squared. And we might have an initial condition at y at x is equal to 2 will be equal to 1. We see right away that this is separable, right? We could form a group here with the x terms and another group here with the y terms. So let's do that. So let's divide both sides by y squared, and this gives us 1 over y squared dy by dx is equal to 2x. And now we can multiply both sides by dx. Which allows us to integrate this equation. So carrying out these indefinite integrals, and I would encourage you to do this on your own, so please pause the video and try this out on your own. Again, these are not the most difficult integrals to solve. We'll find that the left-hand side, the integral is equal to minus 1 over y. And on the right-hand side, we just have x squared plus our constant of integration c. Solving for y, we find that we have minus 1 over x squared plus c. Now to find the constant c, we apply our initial condition. So we know that when x is equal to 2, y is equal to 1. So we substitute x is equal to 2, so we have 2 squared, so that'll be 4 plus c, which leads us to find that c is equal to negative 5. So substituting this into our solution, we find our general solution, y of x, is equal to negative 1 over x squared minus 5. So this was a very simple and straightforward separable differential equation. So again, I just want to be clear that some separable equations are much more difficult to solve in the sense that there are some algebraic tricks that might have to be applied in order to cast it in separable form. And we will look at some of these examples in the upcoming videos.